Okay, so today we're going to be doing congruence transformations and then also coordinate proof, which is actually kind of a relief because we're going to use numbers rather than words to help us show that triangles are congruent to each other. So it's kind of a different take on similar thing, because I think the big thing is that if we're trying to show something, sometimes we use statements and reasons, and sometimes we actually use just words, and then sometimes we use numbers to help us show that. So congruence transformations is a concept that we learned back in, I believe it was chapter 3. But a rigid transformation or an isometry means that a pre-image and an image will be congruent to each other. They just have either reflected, rotated, or translated from the pre-image to the image. And so, of course, those two triangles will be congruent to each other. And the reason why we did that was to talk about, how do we do these types of things and what happens when we do it? What will they look like? Those kind of things. And I think it has been helpful. I'm pretty proud of you guys, how you've been doing this year. All right. So coordinate proof has to do with a style of proof that choose or uses coordinate geometry. So like ordered pair geometry and algebra skills, okay, to help us show that geometric things are true. Okay, so, one thing we're going to talk about would be the area or perimeter, or we're going to be talking about the distance between some points or angles formed. So those would be things that we're going to use Rene Descartes' coordinate system and those principles and some algebra skills to be able to say, hey, let's demonstrate, numerically that these two triangles are congruent. So in the previous couple of sections, we have not used coordinate planes, have we? You notice there's been no graphs. We've mostly been saying, look at these using midpoints, using angle, side angle, or well, not angle, side angle. Yeah, we've been talking about that, but using vertical angles, using reflexive property of congruence, those kind of different theorems and postulates and things from Givens. We've been stating, hey, using these principles, use the 6 ways to prove triangles to show logically that the two triangles have to be congruent. Okay, so if we change it to be on a coordinate plane, we're still going to use angle, side angle, side, those kind of things, but we may also just measure the sides and say, look, all 3 sides are congruent. Okay, by side, they will two triangles have to be congruent. All the angles and all the sides, even though we just proved that the sides are congruent. So we just showed that. So if you have a reflection, it's across an axis, which is called the line of reflection. And so we can put it on a grid and show that that is the case. We can also say, off the grid, we did a reflection between 2 of those. And if you look back in your notes or in your homework, you'll notice many of the shapes are just reflections of each other. Okay. Some are translations. Okay. But most are probably reflections, I would say. Occasionally you'll see a rotation, but on a coordinate grid, these are easier to deal with, because they aren't touching, there isn't overlap, those types of things in general. Okay. So remember, translations have to do with the vector. How many right or left goes in the first blank, and then how many up or down goes in the second part of your vector. And you're going to take that original shape, pre-image, and shift it right or left a certain number of values, points, and then up or down a certain number of points. And then the next one would be, let's rotate each of the points or all of the infinitely many points of a figure through space counterclockwise a certain number of degrees. Okay, and so back in the transformation chapter, we talked about doing 90 degrees, 180 degrees, and 270 using a certain formula for each of those. However, in this chapter, we're going to mostly be saying, okay, just look at the 2 shapes. Can you tell there's a reflection and then a rotation or, translation? And then can you show that they're going to be congruent by doing some mathematical calculations? And so let's just try one right now. Okay, so if we start with the points 1, 2, okay, so 1, 2, oops, I better get a writing utensil. Here you go. So 1, 2, got another new stylus. So we'll see if she's even better than the last one. This is going to be J, and then K is 4, 2. Okay, so that's K, and then L is 1, 3. Okay, yeah, it seems to be working much better. Okay, so we've got a right triangle, it looks like, doesn't it? Okay, 2 of the legs are going to be vertical and horizontal, okay, one of each. And then there's a slanted line that's the hypotenuse of this triangle. So we're trying to say, hey, is that triangle going to be congruent to the second triangle, which will be the image one? And that will be -1, 2. And that point is at, that's point Q. And then R is -4, 2. And then S is -1, 3. You're like, well, obviously they are. You can tell they are. Okay, so, but let's show it numerically, okay? And so an easy thing to do would be, let's look at the corresponding side. So let's go SQ. The length from that is going to be 1 unit. Just look at, count it. You could do the distance formula minus the y's and the x's and square them, and then add them together, and then take their square root. But the truth is, if it's vertical or horizontal, you may certainly count. Okay. And then L to J, JL, that is also 1 unit. Okay, so, the first side, is going to be shown that these two are going to be congruent to each other. Okay, so here we go. These two are congruent to each other. They're each 1 unit. Awesome. So we have a side shown. Okay, that's a side. We can say, all right, well, what else can we do? And a really easy calculation to do would be to go from RQ. So from R to Q, if you count these, it's 1, 2, 3. We could do the distance formula. It's really just 3 units. Vertical and horizontal, just count. It's not a big deal. And then another thing you could do is to go from R to Q. You can just minus the values that you see. So 4 minus -4 minus -1 would be -3. So it's going to be 3. Okay. I should actually show that because I'm really not making sense as I'm talking. So let's try that in a second. So this is going to be also the same as from J to K. And so those two have to be congruent as well. And that's shown right here. And this one right here. And those would be another side. Okay, so these two have the same length as well. Okay, let me show you the distance formula. I can do the distance from like J to K. Let's try from J to K. If you go from J to K, okay, you could subtract the 2 x's. Okay, so 4 minus 1. And then you could subtract the 2 y's. 2 minus 2 is 0. Square. So anytime you have a vertical or horizontal line, the difference between either the x's or the y's, one of them is going to be 0. And so you subtract the 2 x's, you get 3 squared, which is 9. You'll end up square rooting it, so that's going to be 3. So it's kind of interesting that if you just minus the 2 x coordinates or y coordinates, square them, add them to the other one, then take the square root. That is absolutely true, especially on slanted lines, but on vertical and horizontal, you could get away with just subtracting the coordinates or just, counting to see what you've got. So I could have just subtracted 4 minus 1 and gotten 3. Okay. The distance between the 2 x coordinates is going to be 4 minus 1, which is 3. Okay. Same with if you looked at the distance from from R to Q, if you minus the y's, you get 0. But if you minus the x's, -4 minus -1 is -3, -3. Well, you can minus the 2 coordinates and then take their absolute value. We talked about that before. The distance is literally 3. Okay. So that's kind of a nice thing to have in your pocket to talk about how do you find vertical or horizontal distances. You can minus the x or the y as appropriate and then take its absolute value. Okay. Yes, you can do the full-blown distance formula, but it's not really necessary if you're just going to go a vertical or horizontal distance. I will demonstrate from L to J real quickly. To go from L to J, let me erase these guys here. Oopsie, that is not an eraser. I do like my new stylus a little bit better. Okay, so let's try this here. We've got from, let's see, J to L to J. Okay, so if you just notice, they're going to be directly vertical from each other here from L to J, and it's just 1. Well, notice if you subtract the y coordinates 3 minus 2, you do get 1. Okay, minus the y values and then take their absolute value if you need to, and it'll be 1. Okay, so I have two distances shown from that correspond, and that's not enough to show that they're going to be congruent. However, number one, we could find the hypotenuse's length and do side, side, side. Okay, another thing, honestly, do we know the angle between SQ and RQ? Well, yeah, it's got to be directly right angle. Okay, you can tell that their slopes are going to be perpendicular to each other. You can see it from the graph. You can tell from the points. You could calculate it algebraically, but you know that angle Q and angle J are right angles. So angle Q equals 90 degrees, which is, or is perpendicular, okay, which equals, we could write the measure if we wanted to, which equals the measure of angle J. So by side angle side, you know these two triangles have to be congruent to each other. And so as long as you find enough lengths or angles, sometimes angles you can't find because we're not good at figuring out angles based on a graph, but a right angle, we can tell by the ordered pairs. Okay, so this is a reflection. Okay, and then also they're congruent to each other. Why? By side angle side. Okay, congruence. Okay, so the truth is, yeah, absolutely, those two are congruent. Okay, now let's try another one. Okay, here we go. Okay, I went the wrong way. Let's go this way. Okay, so another one will be over here. Okay. So given the triangle, let me find a pen for us. We're going to change up a color or two. I'm going to find a nice little pink maybe if I can. All right, done. Okay. So I've got a nice little pink. So let's do J, which is -3, 0. She's J. And then K, which is -4, 2, 4, sorry, -2, 4. That's going to be K. And then L, which is -1, 0. So if that's our first triangle, okay. Wow, I'm not connecting the arrays nicely. Oh, let me erase these a minute, and let's see if I can draw them a little bit less sloppy. Okay. I'm not sure if I can. I'll try it. Okay, so if you go from K to J, and then from here to here, and then from here to here. Okay, so you got a little triangle. Okay, I shaded it in, but maybe I can make it a little bit better looking. So here we go. Bump, bump, bump. Not really. Okay. It's kind of okay. And then our next one, we've got to do Q, which is 2, -4. It's a good idea to label them with their points. R is 3, 0. And then S, which is 4, -4. Okay, so we got two triangles. Okay, we got to show, hey, what kind of transformation happened? It looks like a translation over some and down some, okay? And we could count those and see, we probably should. But right this second, we're just going to show that these two triangles are congruent and then talk about what happened between them. So, all right, let's start it, okay? So if we do the distance from J to L, okay, so JL, okay, we can just, quite honestly, that does not look like an L, okay. Okay, so to prove these, we need to prove, that they're congruent to each other. So if we do JL, okay, the length of JL is pretty easy. It's 2 units, okay, and that's equal to QS, okay, so JL and QS, absolutely, their lengths are equal to 2 units, so that we've got a side that's going to be congruent to another side. Okay, awesome. The other thing I would say is that, okay, and so we're going to find the other two sides. Okay, so let's find, let me see if I can get this to work for us. I want to get a nice, cute little color. Here we go. Let's do this right here. Let's find the distance from J to K. So to do from J to K, we're going to use the distance formula, okay? I'm going to subtract the two x's, so -3 minus a -2 squared plus the 2y's, 0 minus 4, and then squared. So that'll give us -1 squared, which is 1, plus -4 squared, which is 16. So that'd be the square root of 17. So the distance from J to K is going to be the square root of 17. And so let's do the distance. So she should match with QR. So let's try QR. All right, so QR. So if you take Q and R and subtract those points, let's try it. Okay, so let me grab these guys here. Q to R, we're going to subtract the two x's. So 2 minus 3 squared, and then subtract the two y's. 0 minus a -4 is going to be 4 squared. So that's going to be -1 squared, which is 1, 4 squared, which is 16. Guess what? QR is a square root of 17 units as well. So those guys are going to be equal in length or congruent. So these two match each other. Okay. And then we've got to do the distance from R to S and K to L. So let's try that. I'm going to grab the next color. So let's go from KL. So K to L, and let's see, that would be subtract the two x's. So -2 minus a -1, so +1 and then squared. And then 4 minus 0 is 4 squared. Okay, so that's -1 squared is 1, 4 squared is 16, again, square root of 17. We're not surprised. They look congruent to each other. So this one right here is square root of 17, and then also RS should be the same thing. Okay, so RS would be 3 minus 4 is -1, and that's squared. 0 minus -4 is 4, who is squared, and that's going to be square root of 17. Okay, so we have shown that all three sides are congruent to the corresponding sides between two different triangles. So therefore, these two triangles are congruent. Why? Side, pardon me, congruence. Okay, and that would be a postulate. And then the next thing is the transformation is a translation, and it's translating. Let's check this out. I'm going to take K to R. It looks like you go right 1, 2, 3, 4, 5, and down 1, 2, 3, 4. Okay, so it'd be 5, right 5, and down -4 if you go from left to right. We don't know which one, so it's a translation, and you can say the dimensions if you're like, depending which one it is. So you're going to move them right and down, or if you start at the right and go to left, it should be left and up. There is no given as to which one's the pre-image and which one's the image, but we just know they're a translation away from each other. Okay. The next part is we want to talk about, are these going to be the areas matching? Okay, so the next part is we're supposed to write a coordinate proof with specific values. Okay, and you're like, okay, great. What do you mean? Well, I mean is given right triangle ABC, so the one on the right, and then if D is the midpoint of AC, and what we're going to try to prove or show is that the area of DBC is half the area of ABC. And so we're not going to write formalized statements and reasons. However, what we are going to do is we're going to show it. Okay, so show it numerically that we're doing this. Okay, so it's not as hideous as perhaps it feels like it might be. Okay, so let me look and see if I can get a nice color for us today. Let's see. And one more here. Okay, so as we're doing this, we're trying to say, okay, let's find the area of DBC. So to find the area of any triangle, you take the length of one of the bases and times it by the height that's perpendicular to it. So in a right triangle, we are in luck that the base and the height are going to be aligned with the axes here. So here we go. The base here is 4, and the height is 1, 2, 3, 4, 5, 6. So to find the area of triangle ABC, we're going to take 4 times 6 and then divide your answer by 2. So that's going to be 24 divided, so it's 12. So it'll be 12 inches. Actually, I lied. It'd be 12 units squared. Okay. And so if you count up how many squares are inside that little grid, there's 12. You count the full ones, you can see there's like basically 1, 2, 3, 4, 5, 6, 7, 8, and then like some halvesies and stuff. So that will get us up to about 12. Okay. And it will be exactly 12. If you aligned these together, you'd notice it is exactly 12. Okay. So 12 units squared. And then truthfully, then we are like, okay, well then what about DBC? Okay, well DBC is this triangle right here. And so to find the area of her, we're going to do the base, which is 4. And then notice the height is going to be 3. Wait a minute. The height is half of the height of the bigger shape. So basically, look at this. As we compute it, if we do area of triangle DBC, we're going to, go 4 times 3 and divide by 2. So that's 12 divided by 2, which is going to be 6 units squared. So yes, if you've got the same base, notice they both have the same bases, but the height of the second one is half the size of the other. Well, guess what? The area then will be half the size of the other one. So if the bases are the same and the height is just half is high, it's going to be half the height of the original shape, which is kind of weird. And so it's not something you need to memorize, but I'm just saying, well, there's some logic that's happening, starting with the same base. Okay. The next thing is, can you hear directions and draw what they say? And then can you hear directions, but then also label the vertices of the shapes that you made? Okay, and so there are easier and harder ways to draw them. So some of the hints to make it not as terrible to do. Make sure you use the vertex, place the origin at a vertex. And so if you're making, rectangle, probably rooting it by the origin would probably be a good choice. Okay, or center the figure at the origin. So one of those two would probably be a good choice. And then make a side of the figure close to the origin. Okay. Center a side. So that's a third option. So maybe you will, if you're drawing a shape, you'll put one of the vertices there. Maybe if you're going to, it says, so the second would be center the figure at the origin. Okay, so it might be easier to make the middle of it to be right at the origin. Okay, another one might be the center of the side of a figure at the end. So we kind of did that here. So maybe the center of a figure, let me erase this, being at the origin might look like, say, let me show you, like this. Okay, so you might have some options, okay? You also might use an axis as the side of a figure, okay? Just again, we're trying to make it not hideous when I ask you to write the ordered pairs of the vertices of this. So if you rest it right here, where 2 of the sides actually are aligned with the axes, that probably is a good choice too. Okay, so let's see what they ask us to do here. Let me see, I need to charge my computer. We need to make a square. Okay, so all the sides should be congruent. And we want the side lengths that are 8 units, and we want them with the midpoint of one of the sides at the origin. Okay, so the midpoint. So let me erase this little stinker. Here we go. So we can't really put it how I just had that figure. We have to put the midpoint of a side. So that means half of it is on either side of the origin, okay? So if that side's going to be 8, well, then we have to have each side on the other side of it to be 4. And then if you're going to have to make it a square, well, if the bottom side's 4, that means it's vertically 8 high, okay? So this distance right here is going to be 8 high. And then, so it's plus or minus 4 from the middle, from the origin. So it'll say, tell me the ordered pairs. Okay, well, to get to this right corner of this, we're going to be at the point 4, 0. To get to the point that's just directly north of it, okay, you go right 4, but you're going to go up, say, 8, because we need it to be a square. To get to the left, you're going to go left 4 and up 0. And then to get to the top left corner, you're going to go left 4, and you're going to go up 8 as well. Okay, so it's a good test of like, can you read it? Can you try it? And is your shape actually the shape they ask you to do? Draw a square, so all four sides should be congruent. And is the center of one of the sides at the origin? Okay, how about if we make a circle with radius b? It doesn't say where you got to put it, but I would suggest we put it centered at the origin. Okay, now this doesn't have any vertices, but let's name a couple key points. If the radius is b, this point is the point B0. Okay, if this has a radius of b, this is going to be 0 and then up b. What would be this point? Left b and up 0. How about down here? This is going to be 0 and then negative b. Okay, so it's kind of interesting to see what can we do to make our shape be what they ask us to do. And we need to do a right triangle. So we're going to draw a right triangle, legs that are A and 2A, and the vertex of the right triangle is the origin. Well, I'm going to do it like this. Okay. And actually, that would be a bad choice because one of the legs has to be A and the other leg has to be 2 times A. So one of the legs is going to be twice as long as the other one. So I'm going to go up here and make it twice as long. So if this is our right triangle, if this is A, well, this would be 2A. Okay. And then let's do it. We've got this point would be A comma 0. Of course, this is 0, 0. And this up here would be 0 and then 2A. Okay, cute. The rectangle with dimensions C and 3C, and the origin is at the midpoint of the width of the rectangle. Okay. Length and width are just two of the, the length sides, okay, of a rectangle. So I'm going to make this to be C this way and C this way. And then our height, I'm going to make it to be up 3C. I just have more space than if I do that. So the height is 3C. Okay, up to here. Okay, so this point right here would be right C and up 0. This would be right C and up 3C, okay? This would be left C and then up 0. This would be negative C and then up 3C. There you go. So go ahead and look at the next couple examples and say if you can plug in or write the ordered pairs of what's missing, okay? If this is a right triangle with legs that are equal in size, the point Y is going to be A0. Z is still 0, 0. And then C would be right A, but up, how high? Also A, okay? How do you know? Well, because you go right a certain dimension and go up the same dimension, because notice those legs have that marking that says, tick marks that say, hey, they're same length. Okay, so let's say K is negative A and then up 0. Well, if you have an isosceles triangle, you know that it's going to be very centered. And so this point P is going to be to the right 0 and up 0, or right A and up 0. And then B would be over 0, but up B. Okay, so here we go. Now, the last one we're going to do is we're going to, again, show numerically using a grid. Okay, we're not going to do a formalized proof. We're just going to show numerically from the grid what we've got. So if you have triangle ABC, which is going to be over 2 up 1, that's A, and then 2, 9, that's B, and then C is 6, 1. Okay, so that's C. So we've got a triangle ABC. It looks like it's a right triangle, doesn't it? Okay, so you got a right triangle. And it says D is the midpoint of segment AB. Okay, well, if A is at 1 and B is at 9, then 1 plus 9 is 10 divided by 2. That would be at 5. Okay, so the midpoint is directly halfway, which is going to be right here. So midpoint of D is the midpoint of AB, so that's point D. Okay, cute. So the midpoint of AB is going to be over 2 and up 5. So 2, 5. This is 2, 5. Okay. And find, oh, it's going to ask us to find the length of each side in a second. Okay. Find the midpoint of AC. Okay. And so from A to C, we're going to go 2 plus 6 divided by 2. And we're going to go 1 plus 1 divided by 2. So it was going to be 8, which is 4. And then 2 over 2, which is 1. So 4, 1. 1, 2, 3, 4, 1. Well, I found the midpoint of AC. Yeah, 4, 1. Okay, here we go. And that is going to be E. Okay. Okay, let's find the length of each side. Okay, well, the horizontal one you can just count. So it's 1, 2, 3, 4 units. Okay, so AC is 4 units. AB is actually from 1 up to 9, so that's 8 units. You can just subtract the y coordinate. So if I do 9 minus 1 is 8. Okay, so that's the length of that. And BC, I'm going to have to do the Pythagorean theorem. So I'm going to do from B to C, I'm going to add 2 or subtract 2 and 6, and I get 4. So 4 squared. I'm going to subtract the y's. 9 minus 1 is 8, and 8 squared is going to be 64. So 64 plus 16 is going to be 80. Okay, so the square root of 80. Or we could call it the perfect square who goes into 80 is 16 times 5. So it'd be 4 square root of 5. Okay, so those are 2 things you could write. Or you could take the square root of 80 in your calc and get a decimal, depending on what you're going to actually do with this stuff. So find the length of each side of ADE. So where's ADE? Okay, so we're going to focus on a slightly smaller triangle right here, ADE. Okay. So that means AE is 2 units. AD is going to be 1, 2, 3, 4 units. Notice it's half the length of the previous one. Okay. And then DE is going to be, let's do the quadratic formula. We're going to do D minus E. Let's see. And D is 2, 5, and E has a point of 4, 1. Okay, so let's find the distance between these 2 points right here. So we've got 4 minus 2 is 2. 2 squared is 4. 5 minus 1 is 4. 4 squared is 16. So 16 plus 4 is going to be the square root of 20, which is going to be, so you can write the square root of 20. Or you can say square root of 4 square root of 5, so it would be or 2 square root of 5. Okay, notice if this is 4 square root of 5, half of 4, if you take half of 4 square root of 5, you just multiply the coefficients. If you multiply these together, you get 2 square root of 5. So that's kind of an interesting thing. Okay, so 2 square root of 5 is going to be that or the square root of 20. Okay. And it says, let's find the perimeter of both these things. Okay, so if you do the perimeter of, I'm going to get a highlighter here. You do the perimeter of ABC. So we're going to add up 4 and 8 and 4 square root of 5. Okay, so if you add those, you can only add like terms. Okay, and so it's going to be 4 plus 8 is 12. So it'd be 12 plus 4 square root of 5. And if you wanted the decimal approximation, you could use your calculator. 12 plus 4 square root of 5, and it will give you the decimal approximation. Okay. The perimeter of the smaller one, okay, is going to be, let's check this out. We're going to take 2 and 4 together and add it to 2 square root of 5. And so when we do that, we get 6 plus 2 square root of 5. Notice it's the smaller one is half the size of the bigger one, isn't it? Okay. So therefore it says the perimeter of ADE is half the perimeter of ABC. So notice since the area of, or we're saying perimeter, so the perimeter, of ABC equals 12 plus 4 square root of 5, and the perimeter of triangle ADE equals 6 plus 2 squared root of 5, then you could say the perimeter of ADE is half the perimeter of ABC. Okay, and notice each dimension is half as big, so therefore the perimeter of the big one and the smaller, it's going to be the smaller one's half the size of the other one. All right, well, thank you so much. Have a good day.